It's my pleasure to introduce Professor Sudipto. Just a moment. What is the? Okay, just a moment. Okay. So Sudipto is assistant professor in the LLM Institute of Information Technology, Jaipur, India. And actually, he was the PhD student in the same institute where I did my PhD, and he was something like 2 year junior to me. Okay, so today's talk is Morley FEM for von Kármán control, and this topic is quite related, if you remember, with the talk given by Professor Goody. So Professor Goody was the PhD advisor of Sudipto, and actually he was also the student of Nandakumar. So he was these two guys were the joint advisor of Sudipto. Yeah, Sudipto, so you will be having something like 50-55 minutes, and then last to 5-10 minutes we will keep it for the comments and
Sure. Okay.
yeah. So please share the screen now. Okay.
So
And
I'm sharing the screen, right? Is it visible or no?
no, it's not.
Oh, okay. Let me. Okay. Sorry. So. Screen share. Yes. Oh, yeah. In between, I stopped sharing. Yeah. Okay. Now is
Yeah.
it
No.
coming?
Yes, it's coming. Go to the PDF, please.
Yes. So.
Yes. Can you make it the full screen? It will be better.
Yeah. I'm doing it. 1 second. Yeah.
Perfect.
Okay.
So please go ahead. I am switching off my camera and mic. If you have
Yeah.
anything to say, I will switch on camera and mic again, and I will answer.
Yeah. So. Okay. So first of all, let me thank you, Dr. Ravi Prakash, for this invitation, and also I would like to thank all the faculty members of University Conception. I think maybe the pronunciation is not correct, but please forgive me for that, because yeah. So maybe I can tell University of Conception, Chile. So let me thank all the faculty members of the mathematics department over there. So okay, so in this talk I will be. So am I audible?
Yes, you are audible. No problem. Go ahead.
Okay. Thank you. Okay. So in this talk we will be talking about the Morley finite element analysis for the von Kármán control. That means it is an optimal control problem governed by von Kármán equation. So this is a joint work with Professor Neela Nataraj and Mrs. Devika Shailaja. Okay. So this is the outline of the talk. First, we will discuss the optimal control problem, then the optimality conditions, then Morley discretization, then a priori error estimate, and then numerical result, which will validate our theoretical findings. Okay. So this is the problem. So this is the problem. This is the optimal control problem. So it is basically a mathematical optimization problem. So how is the problem? So we can view like, so we know that this von Kármán equation, this is basically a system of equations, system of fourth order semi-linear equations. So we know that this is a plate problem. These two equations describes a plate problem. So what is the problem? Basically, the optimal control problem is, suppose we have a thin plate. Okay, we have a thin plate. Now we want the plate to bend up to a certain degree, and it should bend in such a way so that so by bending some stress also will be inserted on the plate, right? So we want the bending to be in such a way so that the plate doesn't break down. So basically we want to get a desired bending as well as a desired stress. That stress is known as air stress, so that comes from the physics of the problem. So suppose a priori there is some force F acting on the plate. Now what we want to find a force, say u bar, so that the bending of the plate is close to this side E. So this side E is the desired bending and desired stress inserted on the plate. So we want to get close to this side E. So that is our that is the problem. And what is what is alpha? Alpha is a positive quantity, which is a regularization parameter. So what is the function of this regularization parameter? It is, so it basically regularizes the optimal control. If basically, okay. So let me first tell that the solution of this problem will be, say, psi bar comma u bar. So here that psi bar is known as the optimal state and u bar is known as the optimal control. So the function of this alpha is that it regularizes the optimal control u bar. What does it mean? It means that it ensures, this alpha positive ensures that the optimal control, that is u bar, should have at least h1 regularity, because for the numerical approximation to be meaningful, we need the solution to have certain regularity, so this ensures that this alpha positive, this ensures that the solution should have have at least h1 regularity, at least h1 regularity, so that we can go for the numerical approximation. Okay. So here this omega is a bounded polygonal domain in R2 with boundary del omega. Nu is the upward normal. Okay. So here I was telling that this psi has two components, psi 1 and psi 2. Psi 1 is the displacement and psi 2 is the air stress. Okay. And you can see that in this state equation, the nonlinearity appears in the lower order term. Okay. So it is in the second order term. You can see, so this bracket, this square bracket is known as von Kármán bracket. The square bracket is known as von Kármán bracket, and this is the usual bilaplacian operator, which is a linear operator. Right. So you can see that this is a polynomial type nonlinearity, quadratic nonlinearity. Okay. So this alpha is this. So yeah, and the control, that is the force what we are applying, is coming from this set UAD, which is given by this means U in L2 omega, such that UA is lesser equals to U, lesser equals to UB. Okay. So where UA and UB are two constants, such that UA is strictly less than UB. Okay. So this is like this, and it can be shown that this set is a non-empty convex bounded subset of L2 omega. Okay. So now this UA and UB comes from the real world constraints, because we can't opt for force which is too big, right? So that's why these constraints, this lower and upper constraints come. Okay. This is the picture what I was telling. So we are applying some force F plus U on the plate, and it is bending. So this is like this. So okay. So what are the main challenges for this problem? So the main challenges is, as you can see, that this is a fourth order optimal control problem. So there are mainly two challenges. One is this higher order nature of the problem, that is fourth order, and second one is it is a nonlinear control problem. So since it is a nonlinear, and this nonlinearity of the control problem will make this problem non-convex problem. We'll make this problem as non-convex. So it is not a convex optimization problem. Therefore, the solution is not unique. But if we assume that the solution to be a regular solution, there is some, I will tell what is regular solution. Solution is regular and it satisfies some second order sufficient condition, which we will see later. if we assume that, then that guarantees that the solution may not be unique, but it is at least locally it is unique. Locally it is unique. Okay. So that is the problem arising due to the nonlinearity of the problem, due to the basically due to the non-convexness of the problem, because since it is non-convex, therefore the first order optimality condition that we will obtain, that is not enough, that does not quite characterize the solution, that is the optimal state and optimal control. Therefore what happens, therefore it is not enough to study only the first order optimality system, that is KKT system, Karush-Kuhn-Tucker system. So that is not, it is not enough to study that system only. Whereas had it been a linear problem, it was enough to study the KKT system. It was enough to study the KKT system for the numerical approximation. But here that is not the case. Okay. So and second one is due to the higher order nature. So what happens since it is a fourth order problem, so therefore the finite, if we opt for the conforming finite element approximation for this solution, then the finite element, then it will be numerically very expensive. Why? Because the polynomial degree, either polynomial will be a composite P3 polynomial, that is HCT element we can apply, or we can opt for the Argyris finite elements, which has P5 polynomial degrees. So basically the degrees of freedom will contain the first order derivative of the finite element function. So which is, if we try to do that numerically, when we perform our numerical experiments, that will be very expensive. That will use lot of memory. So that is one problem. And also one more problem is that the solution has the regularity of H2 plus gamma, where gamma is between half to 1. Now, since the interpolation, since the conforming interpolation
Maybe
to define
the slides are moving. For me, the slides are not moving. You are still.
Okay, sir. Actually, I have not. Now, is it?
Now it's coming. Okay, fine.
Okay. Sir, actually, I was not moving. I kept it as it is. Yes. Okay, sir. So yeah. So what happens that the to define conforming interpolation, we need the function to be a C1 function. But if it is, say, H2 plus gamma regularity, it has just H2 plus gamma regularity, where gamma is lying between half to 1, then it may happen that the conforming interpolation of such function may not be well defined. So that is also one more problem. We have, if we try to go for the conforming FEM approximation. Okay. So these are the problems. So therefore what we are going to do, we will be looking for the non-conforming finite element approximation. So we will, the state space we will discretize by applying Morley finite element, and the control space will be discretized using piecewise constant functions. Because we will see that the optimal control will have H1 regularity, so it is enough to in order to obtain the optimal rate, it is enough to discretize by piecewise constants. Okay, like this. And yeah, and then we will derive this a priori error estimate for this state, adjoint, and control variables, and under minimal regularity assumption, that is 2 plus gamma. And then theoretical results are demonstrated by numerical results. Okay. So now let us see some literature survey. So first, if we see just the existence of the solution for the von Kármán equation, existence, the theoretical, that is the PD, not, just the PD at the continuous level. So the von Kármán equation, so that is studied by Barger, Knightley, Searle, and Keshavan. Okay. So they have used basically the fixed point arguments to get the existence of the solution for the von Kármán equation. Okay. Then we come to the finite element numerical approximation. This is finite element approximation for the solution. Finite element approximation for the solution of the von Kármán equation. No control till now, only equation. So for that, first the conforming approximation was for a regular solution. We will see what is a regular solution for a nonlinear problem. So for regular solution, it was first introduced by Franco-Bresci, the conforming finite element approximation. Okay, and then the means Carstensen, Nilantraj, and Gauranga, and also by Brenner and others, they have studied the discontinuous finite element and C0 interior penalty approximation of the von Kármán plate problem. Okay, von Kármán equation. And also the Morley finite element approximation was studied by Nilantraj and Gauranga Madhya. Okay. So one common idea for one common technique for studying the numerical approximation of the solution of von Kármán equation was that they have used the in-soup condition or the Babushka-Bresci condition that we know in order to show the existence of the solution of the discretized nonlinear problem. Existence of the solution of the discretized nonlinear problem. They have used that Babushka-Bresci theorem, and then they have used some fixed point arguments to show the existence and the error estimate. Okay. So in all the three papers, so that is the common technique they have used. But obviously, it is for discontinuous Galerkin, and this is for the conforming, and this is for the Morley. Okay, and then also the mixed and hybrid finite element methods are studied for this problem by Miyoshi and others. So this is that. So yeah, but if we look, so this was the numerical approximation for only the state equation. Now, if we see for the optimal control problem governed by that state equation, then there are some literature, but not many. So what are they? First, Hu and others, they have discussed the conforming finite element approximation for the optimal control problem defined on the convex domain. But as we know that for convex domain, if we assume the domain to be convex, that is omega to be convex, then we don't quite assume the minimal regularity, because if it is convex, then the solution will have H3 regularity, which is not always the case. So that it has this so that thing is there. So now also there are so there is optimal control problem governed by steady state Navier-Stokes equation with and without control constraints, which is studied by Professor Remo and others, and Gunsberger and others, to mention a few. Okay. And then there is one recent paper in 2018 by J.P. Remo, Professor Nilantraj, and Gauranga Madlik. They have studied the conforming finite element approximation for the optimal control problem, distributed optimal control problem governed by von Kármán equation. So this is a distributed optimal control problem, what we are discussing now. So we will, so this work is on distributed optimal control problem. We will see how to do it for bounded control. So So this is the weak formulation. So this is the, if we write the state equation in weak form, so this is the weak formulation where this V is, as we saw, that it is a coupled system of equations. So it is, so V is V cross V, where V is H20 omega. Okay. And yeah, and this A, this capital A is coming from the bilaplacian operator, which is this thing, small a lambda 1 phi 1 plus this thing, where small a is coming from the standard Hessian. Is the bilinear form coming from the standard Hessian. This del square psi is the standard Hessian. Okay. And this lower order term, that is b psi psi phi, which is the nonlinear term, is defined by is turns out to be this. Okay. So you can see that the nonlinearity is there. Okay. Now as I told that, so we assume the solution to be a regular solution. So what is a regular solution? So a solution for a nonlinear problem is said to be regular if the linearized problem around that solution point is a well-posed problem. Right? So if it happens that the solution is a regular solution, then we can apply the implicit function theorem on balanced space to say that around the neighborhood of the regular solution, the control to state operator, that is this G is the control to state operator, it's an invertible mapping. So therefore it is well defined. Therefore this reduced cost functional, what we do for the optimal control problem is a well defined problem, because this G is invertible, as well as it can be shown that it is a smooth function. It's a smooth operator. Obviously it is non-linear operator, not a linear operator. So it's a smooth invertible operator, this capital G. Therefore, this small j is well defined. And it's also a C infinity function. It is also a C infinity functional. It is also C infinity functional. Okay. So, okay. Now let us come to, so since the is not linear, therefore the solution is not unique, as I told. But under that second order sufficient condition, the solution can be shown to be locally unique, which I told earlier. So local solution means this thing that within a neighborhood of that solution, say psi bar comma u bar, it has to be the minimum. This j of psi bar comma u bar will be lesser or equals to j of psi comma u for all psi in some neighborhood O of psi bar, and for all u in some neighborhood O of u bar. Okay. So this is a then we say that the solution, this psi bar comma u bar, is a local solution. So for the purpose of error estimate, we will only consider the solution to be a local solution. We will consider the solution to be a local solution. Okay. That means that within a neighborhood of this psi bar comma u bar, this psi bar and u bar is the minimum. So now let us come to the first order optimality condition, that is the KKT system, Kármán system. So the first one is the state equation. The second one is the co-state equation, which comes from the, if we apply fresh derivative on this reduced cost function, because we have seen that since G is infinity, therefore this is a Fisher differentiable, this J. So therefore we can apply Fisher derivative, and if we apply the optimality condition, then we will get this adjoint variable theta bar. This theta bar is known as adjoint variable, and the first order optimality condition, which is a variational inequality. So this bracket, this ordinary bracket, means this is the L2 product. So now let us come to the second order optimality conditions. So second, so which we need for the numerical analysis to hold, and also to guarantee the local uniqueness of the solution. So this is the second order sufficient condition. Okay. So what it says? It says that we assume the solution psi bar comma u bar is regular, and let theta bar be the associated adjoint state. Then we assume that j double prime of u bar. So this is basically a Hessian. J double prime u bar acting on v square should be strictly greater than 0 for all v in C u bar, where C u bar is some tangent cone defined at the optimal control u bar. So I am not defining that because that definition is little complicated. So I am not going into that. It is some tangent cone. This is going to be some tangent cone. So then what we get, then there exists some epsilon positive and mu positive such that this condition holds. Whenever this psi u means psi is the solution of the von Kármán equation with u with f plus u in the right hand side of it. So psi u is the state corresponding to the control u. So whenever this psi u comma u satisfies this condition, so this clearly shows that if this strictly greater than 0 condition holds, then the solution will be a then this psi bar comma u bar will be a minimum for this problem whenever this condition, this u minus u bar in L2 square plus psi u minus psi bar will be less than epsilon square. Okay, so this is a sufficient. So this guarantees the local uniqueness of the solution. Now, okay, so now what are the so this I have already told the challenges. So the challenges is since the problem is non-convex due to the non-linearity, therefore the first order optimality condition is not sufficient, as I told. So you can see that so you need second order sufficient optimality condition. Now, unlike the linear control problem, the first order optimality conditions are not sufficient to derive numerical approximation. Therefore, we need second order condition here. And also since we are applying the non-conforming finite element method, therefore we are basically approximating the finite element space is not a subspace of the solution space. Therefore we need to define some mesh dependent discrete norm which is defined piecewise, and hence the result does not follow naturally as it follows for the conforming case. And also we will see that we will define we will be needing, in order to do the error estimate, we will be needing to define some nonlinear operator on v plus vm. So that there the analysis becomes little more intricate. Okay. And also we need several boundedness properties of the bilinear and trilinear form, what I told there, that b, small b and capital B, that is the trilinear form, which is coming due to the nonlinearity. And also and one more, this is very important point, that to do the analysis, the error estimate for the optimal control, we need the error estimate for the linearized fourth order problem, which is a fourth order problem, linear fourth order problem, but with lower order terms. So which is not quite available in the literature. So that is also quite intricate. Okay. So especially we will see that in the linearized state equation and adjoint state equation that happens. Okay. So now, if we now for the since we have seen that the it is a nonlinear problem, they are non-convex problem. Therefore, the studying the first order optimality condition will not guarantee as the proper error estimate. So therefore, what we need to apply the second order sufficient optimality condition, and when we do that, we will see we will be needing some auxiliary results. We will see that. So one of the auxiliary results is like this. So this is, you can see, this is an auxiliary state equation. Where so this is clearly this is a von Kármán equation only, where this capital F is small f comma 0, and this u is u comma 0. Okay, so we also need what we need. We basically need the Morley for this auxiliary problem. We need its Morley finite element error estimate. We need that. So this is the Morley finite element discretization for this problem. And and this is the where this I have already defined. This B is A and C is this, B is this. Okay. So so that is the Morley finite element discretization of the auxiliary problem. So this is the result for the well-posedness of the discrete auxiliary problem in a ball centered at u bar. So what it says? It says that let psi bar comma u bar be a regular solution of the state equation. Then there exists, say, rho 1 positive and rho 2 positive, such that what happens that in a ball around u bar and in a ball around psi bar, we can find a solution for the auxiliary state equation. We can find a solution for the auxiliary state equation, discretized auxiliary state equation, and that satisfies this error estimate. Where this NC norm is some piecewise Hessian norm. Okay, and also it satisfies the lower order error estimate. Okay. So what is how do we prove that? Result? So outline is, first we define some nonlinear operator. I was telling earlier, from V plus Vm, where Vm is the Morley finite element space. V plus Vm cross L2 omega to V plus Vm by this thing. Okay, where T is the basically bilaplacian inverse. Okay, is the bilaplacian inverse. And we need this uniform bound of this operator. We need this uniform bound of the so okay, so let me say, so what is this del psi n? Del psi n is the linearization of this nonlinear operator n at the point psi bar comma u bar. So therefore what we need is the operator bound for the inverse norm of the discretized linearized operator in V plus Vm now. So which we have shown to be this we need an uniform bound. So uniform bound means this bound, you can see, this is independent of H. This bound is independent of H. Yeah. So this is what is there, and from there we can show that this inverse of the linearized operator, the operator norm of the inverse of the linearized operator is uniformly bounded. with respect to h, uniformly bounded with respect to h. This we can show. So this is a little complicated thing. So then, yeah. So then what we need, yeah. Then we apply basically some fixed point arguments to show that the existence of the solution in a neighborhood of u bar and psi bar. So for that, what we define this one mode nonlinear map, and we want to show that this nonlinear map to have a fixed point. So that if it has a fixed point, then what will happen? That will guarantee that that fixed point will be the solution for this nh psi comma u, right? So this operator is means we are getting motivation from the Newton-Raphson method, from simple Newton-Raphson method. We are getting the motivation to define such operator, because in Newton-Raphson also we define similar type thing. It is in the function space, but there it is in the Euclidean space. Okay, so the tools being used are these: boundedness of the linear and trilinear forms, error estimate for the biharmonic problem and its Morley finite element discretization, interpolation operator, and these things. And also we can prove this result. This result, what it says? It says it is basically the Lipschitz continuity of the control to state operator. This is basically essentially the Lipschitz continuity of control to state operator. So, okay. Now we can apply similar arguments to find the error estimate for this auxiliary adjoint equation. Okay, this is an auxiliary adjoint equation. So this is a Morley finite element discretization of the auxiliary adjoint equation. Okay. So this is the error estimate for that. This is the error estimate for that. So 1 to h means it is the piecewise h1 now. Piecewise h1 now. You can do it like that. Okay. Now let us come to the control discretization. So till now we have not. So yeah, as I told that since it is a non-convex problem, so that just looking at the first order optimality system will not help us. So therefore, what we have done here, we have discretized. Here we have discretized the control space by piecewise constant functions, and this is the problem. This is the problem infimum of J, such that where this psi m and UH satisfies this discretized state equation. This is a discretized state equation. Okay. So here some printing, some typo is there. A should be means it is a piecewise Hessian bilinear form. It is a piecewise Hessian. It should be A and C. And B should be B and C. It is a piecewise. All are piecewise. Okay. So then we prove this theorem that if psi bar comma u bar is a regular solution of the control problem, then for sufficiently small discretization parameter, the discrete control, that is this problem, has at least one solution. And then we also show that this discrete, if the solution is original our solution at the continuous level, that is psi bar comma u bar, is a local minimum. Then this the solution of this discretized problem, that is psi h bar and uh bar, converges to u bar, and psi m bar converges to psi bar with respect to L infinity norm and NC norm. NC norm is that energy norm. That's piecewise Hessian norm. Okay, piecewise H2 norm. You can view it like that. Piecewise H2 norm. And then we come to the this error estimate, optimal order error estimate for the control and state, for the optimal control, optimal state, and adjoint state. Okay. So now what we have used is that since we have used the second order sufficient optimality condition. So we have what we have used, since the reduced cost functional J satisfies the second order sufficient optimality condition, then applying mean value theorem, we can show that there exists such a delta positive such that this condition holds. This condition holds, right? So these we can show just by applying mean value theorem. It can be shown. So then, yeah, then we apply we apply this result, this estimate, then L2 projection, our normal L2 projection onto the piecewise constant functions, continuous and discrete first order optimality conditions, and auxiliary adjoint estimates, which is, so that I was telling that we need some auxiliary result. So this is that auxiliary adjoint estimate we need to prove this equation, this estimate 5, which is optimal, because U bar satisfies the because U bar has H1 regularity. So then we can apply the auxiliary state estimate, and that Lipschitz continuity of the control to state operator, there this 1 and 2 and this 5, to prove this energy norm estimate for the optimal state, with respect in energy norm, that is the piecewise H2 norm, which turns out to be of order gamma, where gamma is lying between half and 1. That because the solution has H2 plus gamma regularity, right? So, and the, sorry, it is getting down. So this, and the adjoint equation and the adjoint variable will have the similar estimate. That is theta bar minus theta m bar nc is of order gamma. Sorry. Okay. So then we have defined some post process of the discrete for the discrete optimal control. For the discrete optimal control, we have defined to find some. So which we defined this UH bar tilde by this. This is a post process control. We have defined like this, which will give us some superconvergence result. Where beta is between 2 gamma and 2. Okay, because why it is superconvergence? Because you can see that though it has H1 regularity, but still we are getting something more than 1. Right? Because gamma is strictly greater than half. So that is that. And then, and also that this post-process control, this post-process estimate helps us to obtain the lower order estimate for the state and adjoint state variables. Okay, so they are given by this, which turns out to be optimal. Okay. It is 2 gamma. Because in NC norm it was gamma, so in 1-2H or in L2 norm it is 2 gamma. So then this is the numerical experiment. So here we have taken a test problem, and we have seen that this order, this NC norm, the order turns out to be almost equal for the state. For the optimal state, it turns out to be almost 1. And the lower order norm, it turns out to be almost 2. And similarly, and for the control, for the optimal control, that is U bar minus UH bar, it turns out to be close to 1. And the post process control, it turns out to be almost 2. And so that was for the so this was for the square domain, that is a convex domain. Now also for the non-convex domain, that is L-shaped domain, we have taken one example like this. So there also you can see that it will be so in NC norm it is so gamma. So here gamma is something around between 0.5 to 1. So it is the order of convergence is coming like that. And here, so 2 gamma is around, say, 1.2 or 1.3. So it is turning out to be like that. Okay. So this is the means yeah, this is for the optimal control. So this is the numerical experiment. Yeah, and these are the references. So yeah, so this is the first article is the conforming finite element approximation, which was done by Gauranga Malik, Professor Neelatraj, and Professor J.P. Remo. Then we have discussed this paper, the results of this paper by myself, Professor Neelatraj, and Devika Shailaja, which was in and if we want to look for the a posteriori error, so this we have discussed only a priori error estimate. Now also there is a posteriori we have done the a posteriori error estimate for the optimal control governed by the von Kármán equation, which in this year. So you can, if you can look for this paper as well for the a posteriori error estimate. Okay, so thank you for your attention.
Thank you, Sudipto. Thank you very much. So we are having 5 minutes for the commentary and the doubts.
I have one very basic doubt.
Yes,
I'm sorry. So why is the problem non-convex? I didn't really pay attention. So if you can explain again. And
okay, sir. So sir, actually the problem is means one thing is clear, since the state equation is a non-linear equation, so the control
Go to the
state
PDF. Please go to the PDF and then show
okay,
that.
okay. Yeah. Okay. So yeah. So the the state equation is a non-linear equation, right? So the state equation is a non-linear equation. So therefore, so one thing is clear, that the control to state operator, that is a non-linear operator, right? That is a non-linear operator. So that will means we can prove from there that this is a non-convex, means the control to state operator is also a non-convex operator. So like that, sir. I think that is
okay, yeah. And
yes.
sometimes I don't know whether it applies here, but I was just thinking whether you can like in some sense relax by convexification. Have you ever thought of like whether it can be like convexified and then try to solve it?
Okay, sir. Convex. Okay, sir. So convexified it. So actually, sir, yeah. No, we have not thought in that direction, but yeah. So we'll look into it, sir.
Okay,
We'll look into
yeah,
it.
thank you.
We'll look into it.
Sudipto, do you consider other types of minimizations like gradient or Laplacian instead of just L2, H1 or H2?
So, sorry, sir. Can you please repeat your question? I couldn't hear actually.
You are considering psi minus ID only in L2, right?
Okay, sir. Okay.
Do you do grade, because it's a fourth order equation? Do you consider grade psi or Laplacian psi minus
Understood, sir. Okay, sir. I mean that Dirichlet cost functional, right?
That is for the Laplacian, so it's a bi-Laplacian. Do you go to next level? Because such problems are never done, right?
Yes, sir. Yes, sir. We will consider that. We'll consider. But sir, so we'll consider that. In that case, sir, psi d we need to assume, here we are assuming psi d to be just L2. So we
Yeah,
need
psi-
to.
True. Grade psi means it has to be psi d in H1. So it will
Yeah,
be grade psi d.
Yes,
Something
sir.
like
Yes.
that.
Yes, sir. Yes, sir. Yes,
Because
sir.
H1 you do that, but so Laplacian square, you will have up to Laplacian, you will be able to go. In the
Yes,
gradient.
As soon as he will consider gradient, the numerical life will be difficult.
Yeah, the analysis will also will be quite different.
Yeah,
Yeah, but-
exactly. But numerically, it will be much more difficult.
Numerically,
Yeah,
it will be
numerical.
much
So
more
no,
different.
the what will happen, the adjoint equation, will change. The adjoint state will change.
Definitely.
Yeah.
What
And the
about
Laplacian, what Laplacian, in other words, in Laplacian, then I don't think it is studied yet.
Yeah.
For the
Yeah,
gradient, fine. For the Laplacian,
No, gradient is for when you have a Laplacian operator. Here you have a Laplacian square operator.
Yeah.
Is there anything meaningful? Is that kind of thing studied in the literature? That's what I'm
Yes, sir. Yes, sir. We will look into it, sir.
What
Definitely.
about the other type of Neumann type boundary condition? This is a Dirichlet type boundary condition, right?
Yes, sir. Yes, sir.
Because
Okay,
for a
sir.
bilaplacian, psi equal to 0, d psi by d nu is the Dirichlet condition.
Yes, sir. Obviously.
But then
Yes.
there are very plate
No.
equations. You have conditions like you impose conditions on psi and Laplacian psi.
Yes, sir.
There are so many different types of conditions, boundary conditions for the
Yes, sir.
biharmonic.
That will be, sir. That will be interesting problem, because in that case, I think the regularity of the solution will be just H2.
Yes, that will be different. So the whole problem of, because that's the equivalent Neumann condition imposing.
Yes. You mean you are saying that psi 1 equal to 0 and Laplacian psi 1 equal to 0, right?
Yeah, there are so many different types of boundary conditions for the bilaplacian.
Yes. Obviously, that Cann-Hilliard condition is also there.
Yes, because these are all physical.
Yes, sir. We will look into it, sir. Yeah, definitely. And that will be more challenging. Because the solution here, has, even if it is a L-shaped domain, it has 2 plus gamma regularity, where gamma is greater than half. But there it will be just H2. There gamma will vary from 0 to 1, not from half to 1. So that will be more challenging, obviously.
Because there are a lot of problems. If this is the first time you are doing, there will be plenty of problems there.
Yes, sir. Obviously.
Okay, thank you.
Okay, sir.
Good presentation, Sudipto.
Thank you, sir.
I'm happy
Sir,
that
I
you are
thought
present.
I was fumbling in between, so I thought, how was it?
No, that's okay. That's very small compared to earlier. It's very good.
Okay, anybody else? Very quickly. Okay, so there is nobody. So stop here. Thanks again, Sudipto.
Thank you.
Hopefully
Thank
we
you for
will meet.
inviting me. Very nice to see Nandakumaran sir and everyone after a long time. It is a wonderful experience.
And we are happy to see you alive. That's very important.
Yeah.
Thank you.
It's a smart. What's your weight now?
Sir, that I have.
That's a question I want to know.